First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
All right, greetings. So today's lesson, we're looking at area between curves. So the scenario is you have two functions and you're trying to find the area between those two functions. So the problem I have to get us started, it says find the area of the region between the curves f of x equals 6 minus 1 over 5x squared and g of x, which equals negative x plus 5 on the interval 1 to 5. So I want to give you a graphical representation of what this really means. So here I have both graphs. Here I have the graph of both functions. And so you can see there's a graph of f in red and there's the graph of g in green. And we're trying to find the area between these two curves on the interval from 1 to 5. So we're only really concerned with the interval from 1 to 5. And the area between actually means the area between those two. So that shaded region right there, that's the area that we want to find. Now, this type of problem should remind you of area under the curve. So this is very related to finding area under the curve, even though here we're finding area between two curves. So let's just look at the area under the first curve f of x, or the top curve. And you see all that area that you see shaded is the area of f of x from 1 to 5. And again, the area we're trying to get is this area, but the area from 1 to 5 is given there. And again, the definite integral of f of x from 1 to 5 gives us the area under that curve. And then if we look at the area under the curve of g, so this is the area under the curve of g. Again, we get it from the integral of 1 to 5 of g. So that's the area under g, and that's the area under f from 1 to 5. And that's the area that we want. F, G, what we want. So if you look at it, so here are both areas. This is what we want right here. This is what we want. Now all the way down here is F and right here is G. So if we simply subtract G from F, we get what we want. So in order to find this area, we're going to integrate from 1 to 5 f minus g. That's how you find area between the curves. So more generally, you know, the integral from a to b of f of x minus g represents the area between the graphs of f and g, provided f is greater than or equal to g on the interval and f and g are continuous on the interval. In this part about f being greater or equal to g on that interval, we'll discuss, we'll get a look at why we need that provision in one of our examples. Of course, the fact that they need to be continuous is quite obvious if you understand integration. So let's look at the problem and let's go ahead and find the area between the curves of the given two functions. All right, so these are the two functions at hand, and we want to find the integral from 1 to 5 of f minus g. Now, when you're doing this, and there's provision written in there that, you know, f should be greater than or equal to g on this interval, that's pretty important. The couple of reasons. One, we're going to investigate on a subsequent example. But to this example, you know, say for instance, you know, g was the top function. Well, when I do this subtraction, so let's say hypothetically, this is the graph of g and this is the graph of f. So g is the top function, but I'm doing f minus g. So when I find this integral, it's going to be this area that's here. And when I find this integral, it's going to be this area right here. And this area obviously is more the area of G is obviously more than F since it's above it. And so when I subtract, I'm going to get a negative answer. So in order to get the correct area, the area is going to be positive. You want to make sure you're doing the top function from a graphical standpoint minus the bottom function. And that's why we get the provision that F should be greater than or equal to G on the interval. So let's go ahead and plug the functions in and do our integration. So we're taking the integral from 1 to 5 of 6 minus 1 over 5 x squared minus negative x plus 5. And if you want, before you integrate, you can, simplify this, distribute the negative sign and combine like terms, or you can integrate these separately and then subtract them. And you may choose one method or the other depending upon the case. For this particular case, I'm gonna go ahead and subtract them, combine like terms, and then do the integration. So let's see. So I'm gonna have minus a negative x. That's gonna turn to a positive x. And I'm gonna have a negative 5, and that's 6. So that's gonna turn to 1. So I'm going to be integrating from 1 to 5, negative 1 over 5 x squared plus x plus 1. So again, that's just me simplifying this expression, just actually doing a subtraction. So now let's go ahead and integrate. So let's find the antiderivative of this expression. And so the antiderivative of negative 1 over 5 x squared will be negative 1 over 15 x cubed. And for x, we'll get x squared over 2. And for 1, we'll get x. And we'll evaluate that from 1 to 5. So hopefully that made sense. These are all these polynomial expressions. So we just did the power rule for all 3 of these. So now, based on the first fundamental theorem of calculus, we'll plug in 5 for x and plug in 1 for x and subtract those 2 quantities. Let's go ahead and do this on a new sheet. So let me first plug in 5 for x. So 5 cubed is 125. So that's negative 125 over 15. I'll simplify later. Plus x squared over 2, so plus 25 over 2. And then plus 5. So that's what I get for plugging in 5. And so now minus, and now I'll plug in 1 for x. And so if I plug in 1, that'll be negative 1 over 15 plus 1/2 plus 1. All right, so just doing arithmetic here. And I like to deal with the guys that have common denominators. So I'm going to do the subtraction. And that's kind of why I didn't want to simplify this first, because, when you plug in the numbers, your A and B numbers, and you got fractions, you're going to get fractions with common denominators. That will make the subtraction a little easier if you do it with common denominator by common denominator. So I'm going to do negative 125 over 15 minus negative 1 over 15. So that would become plus 1 over 15. And so that would give us negative 124 over 15. And then you have 25 over 2 minus 1 over 2. That's 24 over 2, or 12. And then you have 5 minus 1. That's 4. So let's see how we can reduce this fraction. Doesn't look like we can reduce it at all, actually. So let's leave this like this, minus 124 over 15, and this is 16. And so let's find a common denominator. So let's multiply 16 times 15. Let's see, that's 80. at 16, that's 240. So we have negative 124 over 15 plus 240 over 15. And I apologize, I have this proclivity as I write for it to kind of slant. I really apologize. It's one of the deals of the struggle. And so let's see, when we add these two together, that's 116 over 15. So that is the area between those two curves. All right, we're going to look at another example. And this next example, there's a couple of things that I want to point out, and that's dealing with the provision of, with the definition we gave, where we said that, f of x should be greater than or equal to g on the whole interval. So we're going to bring another instance where that particular provision is important. All right, so this is example number 2. And so here we have two functions, f and g, and it says find the area between the curves on the interval 0 to 3. Now, there might be a situation such as this, because again, in the deal, we said, when we do the integration, we want to do the top curve minus the bottom curve in terms of a graphical analysis. And it doesn't mean, don't assume every time they give you two functions that the first function they give you is the top curve and the second function is the bottom curve. So that's not the case. And it might be a little difficult for you to figure out, which one is actually on top and which one is actually on bottom. Or you may be able to figure it out, but I don't know if it may take the time that it takes to figure it out may not be worth it. So, if we think about these two curves, f of x is obviously an upward facing parabola. So it's something like that. And g is obviously a downward line. And so it's something, like that. And just because this slope here is negative, you can't necessarily assume, for instance, the vertex of this guy is not at the origin. So I can't assume that the graph looks something like this, where f is on top and g is on bottom. So sometimes it may be difficult to kind of figure out, or maybe too time consuming, plot various points to try to figure out which function is on top and which function is on bottom. If that's the case, I always say don't really worry about that. How you can save yourself is simply, and there's another thing I need to take in consideration on this problem for right now, but for this statement, I'm going to assume the other thing I need to take in consideration is not relevant. So if I have these two curves and I'm not sure which one is top and which one is bottom, what I can do to save myself if I'm doing an assignment is simply just integrate from a to b f minus g in whatever order you want. So again, this is the case where I don't know which one is on top, or I don't feel like figuring out, and then just take the absolute value of that number. So that covers you. So that will give you the actual error, whether f was top or g was top. So that's the way to cover yourself if it's not obvious which function is the top function and you don't feel like wasting the time to figure it out. Okay, but there's another thing with this situation that's important. So it wasn't germane on the first problem, so we didn't even bring it up. But on this problem, so when I ask you to find the area between two curves on a particular closed interval, you should always make sure that the functions don't intersect inside of this interval. Or rather, you should try to find if there's any points of intersection within this interval, because that changes things. And why is that? So let's just take the shape of these two curves, for instance, and we'll look at the actual graph of these curves in a second. So let's just say, for instance, let's just say the graph is like that. And let's just say, hypothetically speaking, and we'll look at it in more general terms in 1 second. And of course, this is the graph, in more specific terms in a second. This is f here, and this is g here. So let's just say that the interval AB, looking for a pen of a different color. So let's just say that the integral AB, and let's just say this is A here, and this is B there. So from here to here, this point of intersection, F is on top and G is on bottom. But look what happens after they intersect. Now G is on top and F is on bottom. So when a situation like that occurs, you got to do two integrals. One from A to this point of intersection. Let's call this point of intersection C. So one from A to C and the other from C to B. And to do it properly, of course, on the first integral, it should be the top function minus the bottom function. And on the second integral, again, it should be the top function minus the bottom function. And so the order should switch there. But again, if you want to get away from worrying about switching the order, all you have to do is put it in an absolute value symbols. And that's kind of the way, that's the way I'm going to do it here. So I tend not to waste a lot of time trying to determine which function is on top and which function is on bottom, unless of course it's quite obvious and it doesn't take me a lot of time to figure it out. When it takes a little time, I just integrate with the absolute value. But even that, so if there's a point of intersection within the interval from A to B, you're still going to have to integrate twice, particularly when doing the integration by hand. So let's first check if there's a point of intersection between 0 and 3 here. And then we'll take a look at the graph so you can kind of see what's happening. And then we'll go ahead and find the answer. Now, of course, if these two functions intersect, at the point in which they intersect, there's an x value where both the functions are equal at that particular x value. So to find the point of intersection, I will simply set the functions equal to each other and solve for x. So let's go ahead and do that. So we'll say 6x squared minus 14x is equal to negative 8x. All right, so we're just going to solve for x. So we'll add 8x to both sides, and we'll get 6x squared minus 6x equals 0. We'll factor out a 6x. We'll get 6x times x minus 1 equals 0. And so the intersections are at 0 and 1. So 0 is no big deal because we're integrating between 0 and 3. But the fact that it intersects at 1 is a big deal. So that means when I do this integration, I'm going to do one integral from 0 to 1. And I'm going to write it like this because I'm not going to even change the order in which I integrate. So f of x minus g and then also, and I'm really going to do the same thing, f of x minus g, absolute value. So of course, again, just to reiterate, to do this properly, there should be an order change between these two when there's a point of intersection such as this, where they change on who's top and bottom. But if I just take the absolute value of each, I'm allowing myself not to have to worry about that. So in basic, since I didn't change the order, when I do these and I wrote 0 to 1 twice, 0 to 1 here and 1 to 3 here. Apologize. So when I do these integrations, because I didn't switch the order, one of them is going to be negative and one of them is going to be positive. And the one that, of course, comes out negative, that's just the one where the order was wrong. And so I'm just going to, of course, take the absolute value of that guy. And of course, the one that's positive, that's the one where the order was right. All right. Now, before we integrate and get these answers, we'll take a look at the graph of this function so you can kind of see why we have to integrate like this. All right, so here's a look at the graph. And as you can see here, the graph in red is 6x squared minus 14x, which I think was f. And the graph in blue is negative 8x, which I think we call g. And if you look at it, again, there's a point of intersection right there when x equals 1. So from 0 to 1, we got g on top and f on bottom. But then when x gets to 1, they intersect. And then after they intersect, from 1 to 3, we now have f on top and g on bottom. And this is, I kind of zoomed in on the area. When you look at it from afar, it could be a little difficult to see, depending on what type of calculator you're using, if you were graphing this with a calculator. And again, if you were doing this by hand to kind of determine, which guy is on top, this one is slightly on top on this interval. So again, it may be difficult to do or a little more too time consuming. So that's why when it's not completely obvious, I don't even waste time on figuring out which one's on top and which one's on bottom. I just take the absolute value and I don't even switch the order as I integrate. But this is the reason we have to do these two integrals, because if I just integrate it from 0 to 3, the whole function all the way through, depending on how I did it, it would give me one positive area and then one negative area. So depending which order I did it, either it's going to make this area negative and this area positive, or it's going to make this area positive and this area negative. But the accumulation of those two areas is not going to be the real area between the curves that we're looking for. And so that's why we have to do these two integrals in order to get the answer. So let's go ahead and work it out. And as we work it out, I'm going to show you the benefits of not really worrying about which function is on the top and which function is on the bottom, and when doing it with the absolute value style. One thing I want to point out before I get started. So when you go through the work of finding the point of intersection, so, remember to do this, what I did is I subtracted or added 8x to both sides, which is subtracting a negative 8x. Basically, when you set the difference of set this equal to 0, basically what you did is you subtracted the two functions. Now, depending on how you did it, I don't know which one you subtracted, but basically you subtracted the two functions. Well, in this case, I believe this was f and this was g, so we did f minus g. So that equation that you got that set equal to 0 when you're finding the point of intersection, that's essentially what you're integrating. This guy is the equivalent of f minus g. So this is what I'm going to integrate. And the beauty of not worrying about or switching the order in which I'm subtracting is, in both cases, I'm integrating the same exact thing. And so my antiderivative is the same exact thing. And so it's just plugging in different numbers. So that's one of the benefits of just not really worrying about which one is top and which one is bottom, and keeping the order the same for both integrals and just taking the absolute value. So what we have is we're going to integrate 6x squared minus 6x from 0 to 1, and we're going to take the absolute value of that number, and then we're going to integrate the exact same thing from 1 to 3, and we're going to take the absolute value of that number. So that's the problem. So let's go ahead and find the antiderivative. So again, these are just polynomials, so it's just power rule. So the first guy, the 6x squared, that would be 2x cubed, and the minus 6x would be minus 3x squared. That's the antiderivative in both cases. So here we're going to go from 0 to 1 and take the absolute value. And here we're going to go from 1 to 3 and take the absolute value. And also a good thing that makes the process pretty good, when we integrate from 0 to 1, we'll already know what the value is for 1. And so when we come over here, we're really just finding the value at 3 because we already know the value at 1. All right, so let's do the work here. Now, of course, when I plug in 0, it's just going to be 0. So the only thing I have to plug in here is 1. And when I plug in 1, that's going to be 2 minus 3. That's negative 1. So we're going to take the absolute value of negative 1. And I'm just going to leave in the absolute value for right now, plus. So first, I'm going to plug in 3. Now, if you notice, on this one, I got a negative number. So that means this one, and again, we did F minus G. So that means this one was in the wrong order, in which we kind of know if we take a look back at the graph. Because again, in the beginning from 0 to 1, G was the top function. So, and we did F minus G for the whole deal. So that the first part was in the wrong order. So that's why we got that negative number. So that means since this number was negative, that means that this one is going to be in the right order and this number is going to be positive. All right, so let's go ahead and plug in 3. So if I plug in 3, that's 27 times 2, that's 54. Minus, this is 9 times 3, minus 27. So that's what I get in for plugging in 3. And then minus what I get in for plugging in 1. And I already know when I plug in 1, I get negative 1. So let's go ahead and take the absolute value negative 1, which is 1. And this one, we're not going to need to take the absolute value because it's going to be positive. So 54 minus 27 is 27. Minus negative 1 is plus 1. So this is 28. And so the area between this curve is 29. All right, that completes this first video. We're going to do another video on area between curves, but that completes what we're going to look at on the first video. And in the second video, we'll just do some more examples and look at some different type of scenarios that we need to address. So in conclusion, just want to remind you, when you're finding area between curves, if they give you a closed interval to find the area between, always check to see if there's a point of intersection within that interval. If so, you're going to have to do more than one integral, depending on the number of points of intersections that are in that integral. And to not get overly consumed about which function is on the top and which function is on the bottom for any particular subinterval, all you have to do is take the absolute value of each integral when doing this process. And it makes the process a lot easier and for you to find the answer in a more time efficient manner. So we'll stop there and we'll see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.